All right, let's dive into a real classic coding problem today. It's one of those that seems pretty straightforward at first, but hiding just beneath the surface is a solution that is just so clever. It's a huge favorite in coding interviews for a reason, and really mastering it teaches you a super powerful way to think about algorithms.
So let me ask you this. Imagine you've got this long chain of items, right? But here's the catch. You are only allowed to walk along it one time. How in the world could you possibly figure out how to grab, say, the fifth to last item if you don't even know where the end is yet? That's the puzzle at the heart of what we're solving today.
Okay, first things first. Let's break down exactly what the problem is asking us to do. No ambiguity, just a clear goal.
So here's the official problem statement. We're given a singly linked list, that data structure where each little piece, each node, only points forward to the next one in the chain. We're also given a number. Let's call it n. Our job? Find the nth node from the end of that list and just snip it out.
Let's make this totally real with an example. Say our list has the numbers 1 through 5 all linked up, and let's say n is 2. That means we need to find the second node from the end. So you count back from the end. The last one is 5, which means the second to last one is 4. Boom. Node 4 is our target. And this is what we want to end up with. You see? Node 3, which used to point to 4, now just hops right over it and points directly to 5. The chain is reconnected, and node 4 is effectively gone. Mission accomplished. Now, when you first see this problem, there's a pretty intuitive way to solve it. It's what most of us would probably think of first, and it works. But it's a little bit clunky. This method means you got to go through the list twice. On the first pass, you walk from the beginning to the end, just to count how many nodes there are in total. Let's say you find 10. If you need to remove the third from the end, you can now do the math and realize that's the seventh from the start. So you go all the way back to the beginning and walk through the list a second time to find and remove that seventh node. It gets the job done, but it just feels inefficient. And this really lays it all out, doesn't it? The brute force way takes 2 full trips down the list, but the smart way, the way we're about to explore, does it all in one. It's the difference between just getting it done and getting it done with style. So, how do we pull this off in just one pass? Well, it is time to reveal the secret weapon for this kind of problem, the 2-pointer trick. Here's how it kicks off. We create 2 markers or pointers. We'll give them fun names, fast and slow. Now think of these like 2 of your fingers. At the very beginning, you place both fingers right on the very first node of the list. They start together. Now for the brilliant part. You take your fast finger and you move it forward n steps. So in our example where n was 2, you'd move that fast pointer 2 nodes ahead. Meanwhile, the slow pointer hasn't moved an inch. This creates a fixed gap of n nodes between them. And this gap is the key to everything. Okay, once that gap is set, we start moving both pointers forward at the exact same time, one step at a time. The fast pointer moves one node, then the slow pointer moves one node. They travel in perfect lockstep, maintaining that same exact distance between them as they cruise down the list. And here is where it all clicks. The second our fast pointer hits the very last node in the list, we stop everything. And because we created that initial gap, guess where our slow pointer is? It's perfectly positioned, sitting right on the node before the one we need to delete. So all we have to do is tell the slow node to skip over its neighbor, and just like that, the target is gone. A flawless one-pass solution. But wait a minute, great algorithms always have to handle those weird, tricky situations, the edge cases. And this one has a classic trap that's easy to fall into. So what happens if the node we need to remove is the very first one in the list? Say the list has 5 nodes, and we're asked to remove the 5th from the end, which is the head. Our whole logic was that the slow pointer needs to land on the node before the target, but there is no node before the head. Our whole system just breaks down. The fix for this is a wonderfully simple and honestly beautiful technique, the dummy node. We literally just invent a new temporary node and stick it on the front of our list right before the original head. This dummy node becomes our new universal starting point. And here's why this is so brilliant. We now start both our fast and slow pointers on this new dummy node and just run the exact same logic. Now, if we need to remove the head, where does our slow pointer land? It lands gracefully on the dummy node, which is in fact the node before the head. This one tiny trick makes our algorithm totally robust. It works for every single case.
All right, we've got the logic, we've handled the edge cases, we are ready. Let's see how this elegant idea actually translates into real code.
Taking a look at the Python code, you can see our steps perfectly laid out. First, right here, we create that dummy node. Then, we initialize both fast and slow to point to it. This for loop here, that's what moves fast ahead to create our gap. Then this while loop moves them both in lockstep. And this final line, slow.next equals slow.next.next, that's the magic snip that does the removal.
Now, hopping over to the Java version, yeah, the syntax is a little different. We have to be more explicit with types like list node. But look closer. The core algorithm is exactly the same. We create a dummy node, set up our 2 pointers, move the fast one, move them in sync, and then reconnect the list. The pattern is identical. And, you guessed it, it's the same story in C++, where we're working directly with pointers. The little details of the implementation change, but the fundamental logic, it's exactly the same. This really proves that the 2-pointer technique is a core problem-solving pattern, not just some trick for one specific language.
So when we break it all down, what's the final score? Well, the time complexity is O of n because we only make that single pass through the list. And the space complexity is O of 1, or constant space, because all we created were a couple of extra pointers and one dummy node, no matter how massive the list gets. That is incredibly efficient.
So if there's one thing to walk away with, it's this. The 2-pointer technique is an absolutely essential tool for your problem-solving toolkit. It can take what looks like a complicated multi-pass problem and just transform it into a clean, beautiful, single-pass solution.
And that leaves us with one final thought to chew on. This idea of creating a fixed gap between 2 pointers, it's not just for this one problem. So I'll ask you, what other tricky puzzles involving linked lists, maybe finding the middle element, or even detecting if there's a loop, could this same powerful technique help you unlock?